Okay, today we're going to talk about related rates. Related rates are complicated the first time through. And like optimization, it is nearly impossible to give you all possible scenarios. Anyway. But so when we were doing optimization, you got everything in terms of one variable. When you're doing related rates, that won't necessarily be the case. But you do need to pay attention because there will be times when that will be necessary. So one thing that we talk about is the rate of change in volume with the respect to the rate in change of the radius of a spherical balloon. In order to do that, you have to know the formula for the volume of the sphere, the surface area of a sphere, the volume of a cone, the volume of a cylinder, all of those little formulas that you may or may not remember from geometry and before are going to creep up in these problems, and they usually provide them on the AP exam. So we're going to start with a super simple example. Suppose y equals 5x squared minus 6x plus 2. We're going to find dy dt, which is the derivative of y with respect to time when x equals 4, given the dx dt equals 2 when x equals 4. Now we are being given right here a specific rate of change at a specific x value. It is really important to notice that this is not always the rate of change of x. Okay, so we go in and we simply find dy dt. I'm having a few issues with my iPad. Give me a second. Okay, so we know that dy dt would be 10x dx dt minus 6 dx dt. Okay, and we're going to look at that when x is 4. And this, I think I've mentioned this before. I do not remember this kind of notation when I was in high school or college, but it's become pretty standard notation to put this big line with the x equals 4. Very convenient way of keeping track of what you're doing. We, or maybe I should say not convenient, but simple. Pretty straightforward. So we have x equal to 4, and when x is 4, dx dt is 2, and we see that we have 80 minus 12, which is simply 68. And then we look at our problem and we see if we have units and we don't have units. So that doesn't really make very much sense. But if you wanted to, you could say, I don't know, y units over t units. I don't know. 68, that doesn't even make sense. But anyway, okay, example 2. So I hope it was fairly obvious there in example 1 that was a super simple decontextualized problem to introduce the whole concept. Now we're going to look at a balloon. And these, from here on out, you're going to see examples of where an engineer would actually use related rates. And granted, these are not as complex as what most engineers would actually use, but in any case, because I don't think engineers usually run around playing with balloons, although they do. but a balloon is being inflated at a rate of 10 pi cubic feet per second. At what rate is the radius changing when r equals 2 feet? The volume of a sphere is given by the formula V equals 4/3 pi r cubed. Fun fact, one year one of my groups for their final project, which I do have a final project in calculus, decided to do their final project on the rate of change of the radius and the volume of bubbles. It was crazy. It was a lot of fun. It was terrible mathematically, but it was a lot of fun to have bubbles in the classroom. D over dt. Oh, I'm sorry. I lost track of the problem. The volume of the sphere, blah, blah. Okay, so we're going to take the derivative with respect to t of the volume. And let's see, what do we have? We have dv dt, which is 10 pi cubic feet per second. And we're looking for dr dt. So this right here is dv dt. Oops. And we're looking for dr dt. And we have a lot of information right now. We know we can actually find our actual volume when r is 2. We don't need it right now at this very moment, but we could if we needed it. And we know that dv dt would be 4/3. I'm so sorry, I don't know why I said 4/3. 4 pi r squared times dr dt. And we know what r is, and we know what dr dt is. So, still a relatively easy problem. dv dt was 10 pi cubic feet per second. And r was 2. And dr dt is what we're trying to find. So we go ahead and solve for dr dt. Okay, so I can never remember what dimensional analysis. That's what I keep trying to remember from how you learn how to convert your units in chemistry these days. Okay, so we go ahead and solve, and we find that we have 5/8 feet per second. Remembering that down in here, this particular unit right there, that's square feet. That's how it turns into feet per second. So using dimensional analysis, you should be able to get your appropriate units. I personally eliminate units almost immediately. I don't even include them. I personally would not have bothered writing that or that. I would have just included it in my answer because I know what my units are supposed to be, and I'm too afraid of making some sort of linkage error between my original question and my actual answer. So I like to deal with numbers, decontextualize numbers until I get to my actual answer and make sure that I actually answer the question correctly. Okay, example 3, a ladder 10 feet long is leaning against a wall 8 feet high. So we've got 10 feet here and 8 feet here. And the upper end is projected over the wall. If the lower end of the ladder slides away from the wall at a rate of 2 feet per second, so it's zipping along. Oh, that line didn't show up. What? That's so weird. If the lower end of the ladder slides away from the wall at a rate of 2 feet per second, I put the line in the wrong place anyway, so it's a good thing that didn't work out. So this is moving along at 2 feet per second. Boom. Find the rate at which the upper end of the ladder is approaching the ground. So what that means, if the ladder is moving out away from the wall, the ladder is also moving down, and we're trying to find that rate. Now what you should be able to see, theoretically, you should be able to see that you have a 3, 4, 5 triangle here, and at this particular moment in time, the moment at which the ladder starts moving, this distance right here is 6 feet, which makes it a terrible drawing, but we won't go into that. It's enough to trust the math or the numbers more than the drawing. Okay. When you're doing these problems, it's really important to think about what is changing, what is not. No matter what, that ladder is always 10 feet high. How high up the wall is, how high up the ladder, how high up the wall of the ladder is, changes because it's sliding down the wall, and how far away the ladder is from the wall changes because it's sliding away from the wall. So we have x squared plus y squared equals 10 squared, no matter what is happening. If the lower end of the ladder slides away from the wall at a rate of 2 feet per second, find the rate at which the upper end of the ladder is approaching the ground when the upper end reaches the top of the wall. So we have 2x dx dt plus 2y dy dt equals 0. That ladder is not changing. Now, when we go ahead and try to figure that out, at this particular moment in time, we know that x is 6, dx dt is growing, so that's 2, and y is 8 at this particular moment in time. So what we see here is 24 plus 16 dy dt, and our dy dt should be negative because that's shrinking, and it will be. So dy dt is, negative 3/2, and it is negative 3/2. We got to go back and think about our units. Again, I don't like to put in my units until the end. So what's our actual question? Find the rate at which the upper end of the ladder is approaching the ground. Negative 3/2. I just pushed a button. Okay. Negative 3/2 feet per second. Is how fast it's going, the ladder is moving down that wall. Okay, so ladders tend to be pretty straightforward. It is confusing to try to figure out when to differentiate. You usually set up the whole thing first before you start to differentiate. And sometimes, so like this, on this ladder problem, on this particular ladder problem, you use the Pythagorean theorem. Sometimes you're going to need to use trig functions. Balloons are pretty straightforward. Then we get into a woman on a pier. I can't talk tonight. A woman on a pier pulls in a boat using a rope fastened to the bow. She pulls in 5 feet per minute of rope. She holds the rope, that's supposed to be a rope, not a rote, 15 feet above the fastening on the boat. How fast is the boat moving when, oh my gosh, what are these typos? It is 20 feet away from the pier. Okay, so let's think through this carefully. No matter what, that rope is 15 feet above the fastening on the boat. So we're talking about this right here is constant. And we're not thinking about an angle anywhere in here. So breathe easy, Liberty. No I'm sorry, I'm using the wrong, no trig. There we go. So we've got x squared plus 15 squared equal to r squared. And we take our derivatives or we differentiate. And differentiate means take your derivative. Somebody always asks me that really late in the year, and I'm like, haven't you been listening? I've been saying differentiate since day 0. Okay, not quite, but okay, so there's our whole entire setup. And we know that we're looking at what is happening when x is 20. We're looking at that particular moment in time. And we know that at that particular moment in time, she is pulling in 5 feet per minute of rope. She's pulling in that quickly. So that is our dr dt. She's pulling in, so it's shrinking. So dr dt is negative 5 feet per minute. Oh gosh, my cat just fell from a shelf. I don't know how she did that. And x is 20 feet. And what else is happening here? Okay, give me a second. I gotta find out what happened to my poor cat. So I went ahead and figured out what R was, because why not? Basically, I'm not even gonna lie. But we have, I do turn out to need it, just to be clear, because we have this up here, which I didn't highlight very well. Yeah, well, it doesn't circle very well. We have that up there, and we have dx dt. Oh, I'm sorry, we don't. We have dr dt, which is negative 5, and we're looking for dx dt. So in order to use this equation up here, we need r, because we need to solve for x. So we go ahead and we put in 2 times x, which at this particular moment in time is 20. And we're looking for dx dt. And then we use our r value, which is 25. And dr dt is negative 5. And we go ahead and we solve for dx dt, which would be 50 times negative 5. Well, I'm not going to do all that because that would be a waste of energy. 2 times 25 times negative 5. all divided by 2 times 20. And this is why it's a waste of energy. The 2's cancel. These cancel. We have 4 here, 5 here. So that's negative 25. Y'all, I don't know what just happened. Negative 25 over 4 would be dx dt. And now we need to answer our actual question. And our actual question says, how fast is the boat moving when it is 20 feet away from the pier? Well, it's moving negative 25 force. What is that? Feet per minute. And that is how quickly it is moving towards the pier. Okay, example 5. Okay, now we really need to think this through. We know that we have a car traveling at 80 kilometers per hour and it reaches the intersection a half an hour before the bus that is traveling 60 kilometers per hour on the other road reaches the same intersection. How fast as the crow flies are they separating 1 hour after the bus crosses the intersection? Well, the bus crosses the intersection when the car has already driven 40 more kilometers, and then after an hour it has gone 80 more kilometers. So after the hour that we're looking at, the car has already driven 120 kilometers and the bus has driven 60 kilometers. This is at the moment that we are looking at. So we're looking at how quickly they're coming apart in their distance right here. And the distance between the two of them at that particular point in time is the square root of 120 squared plus 60 squared, which simplifies to 60 square root of 5. This is 1 hour after the bus reaches that intersection, or 1.5 hours after the car crosses that intersection. So we go back and we think about what's going on here. We have a right triangle where b squared, the distance from the intersection of the bus, plus c squared, c being the distance from the intersection of the car, will equal d squared, or the distance of the bus from the car. So when we go ahead and differentiate, we have the rate of change of b, we have the rate of change of c, and we have d. So we have everything we need except for the rate of change of the distance between the car and the bus. So we actually have a lot of information here, and we don't need to worry about replacing one variable with another. All we need to worry about is, this is kind of confusing. I knew there was something funny. DD, what? I'm just going to call it that. And B, at this particular point in time, 1 hour afterwards, B is 60. And dB dt, for some reason, maybe they're autopiloted. The bus is, oh, sorry. I'm so easily distracted by myself. DBDT is 60 kilometers per hour. And the car is 120 miles from the intersection. And it is going 80 kilometers per hour. And the distance between the two we discovered was 60 square root of 5. And we're looking for dddt. Boom. Go ahead and solve. And you go ahead and simplify that. And if you're a weird factor like I am, you simplify it in the manner that you see in front of you. And you get that the rate of change of the distance here is 9.387 kilometers per hour. Okay. Gas is escaping a spherical volleyball at a rate of 4 cubic centimeters per minute. How fast is the surface area shrinking when the radius is 24 centimeters? So write down everything you know. Everything you know is that the rate of change of the volume is 4 cubic centimeters per minute, and it's shrinking, so that would be negative. You know that the volume of a sphere is 4/3 pi r cubed, and the surface area of a sphere is 4 pi r squared. It's asking how fast is the surface area shrinking when the radius is 24 centimeters. So in order to figure out how fast the surface area is shrinking, meaning we want ds dt, but in order to figure out what ds dt is, we need dr dt. And in order to find dr dt, we can use our dv dt, which we know in the initial problem, and we can just use our formula for dv dt, or I'm sorry, our formula for volume, which was 4/3 pi r cubed. So dv dt is 4 pi r squared dr dt. And we know that dv dt is -4. And we also know that our radius that we're looking at is 24. And from here it becomes a fairly simple problem. We have -1 over pi times 24 squared, which would be dr dt. And if you're me, you don't do any more work, because you don't necessarily think you need to simplify beyond that. You might not have to. I'm a big fan of factoring. Here we have 8 pi, and our r value was 24. And our dr dt was -1 over 24 squared pi. And look at that. Our 24s cancel, our pi's cancel, and we have 8 times -1 over 24, which simplifies to -1/3. And you see here that the surface area of the balloon is shrinking at a rate of 1 square centimeter per 3 minutes. Okay, people don't like these, but I find them fairly straightforward. The ones that I don't like and most people despise are the shadow problems, which is going to be our next example. Water runs out of a conical tank at the constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5 feet and the height of the tank is 10 feet. So draw all of that first. Once you've drawn everything that's going on there, you need to think about what's going on. We have a formula for the volume of a cone as 1/3 pi r squared h. We also have this random shrinking going on. What's shrinking? The height. So dh dt is -2 or -2 feet per negative crap. That's wrong. dv dt. I don't know what I was thinking. That's the wrong drawing altogether, Marty. Let me see if I can erase it. I don't know if I can. I can't. I'm gonna mess up everything, aren't I? Yo. This is the first time in a long time that I've done this spacey. You know why? It's 9:30 at night. It's past my bedtime. Oh, I'm so sorry. I'm so sorry. I'm so sorry. Okay, there. Redraw. There we go. Okay, so dv dt is -2 cubic feet per minute. Now, what you'll notice here is nowhere in here does it say anything about the radius, except for the value of the radius. All you care about is what's happening with the height shrinking. Well, you know what else? This is like a major revelation in the world of mathematics. No matter where you are in this tank, it's not really a major revelation, just to be clear. No matter where you are, like let's say we're here. If this is 1 foot, that's going to be 2 feet. That was weird. Okay, so you have similar triangles no matter where you are in there. So you know that your height is always going to be twice your radius, or your radius is always going to be 1/2 your height. So look at that. Now you can go back in, zoop, and you can decide to rewrite that whole thing as volume equals 1/3 pi 1/2 h squared h. Oh my gosh, the problem just got so much easier, because all of a sudden all you need to find is dh dt. You have r, you have h. What? You have dv dt, so your volume is 1/3 pi h cubed over 4. Let's make that a little prettier. Pi over 12 h cubed. And we're going to differentiate that. dv dt equals pi over 4 h squared dh dt. And we are looking at How fast is the water level sinking when the water is 4 feet deep? Well, dv dt is always and forever -2, and h, it says right in front of us, is 4, and this is going to give us dh/dt. And I'm sorry this video is so long. And we get -2 equals 4 pi dh/dt. So -1 over 2 pi is dh/dt. So the water level is sinking at a rate of 1 over 2 pi feet per minute. Okay, folks, now we're moving on to a shadow problem. Our favorites. So shadow problems almost invariably involve similar triangles. A man 6 feet tall walks at a rate of 5 feet per second towards a light pole 16 feet tall. That right there should seem fairly straightforward. That first sentence should not be a struggle. It's the next part that frustrates people. At what rate is the tip of, he's walking toward a light pole. Okay. At what rate is the tip of his shadow moving when he is 10 feet from the base of the light? At what rate is the length of his shadow moving when he is 10 feet from the base of the light? See the conundrum? Part of what makes this mind-boggling is that the man is not always 10 feet from the pole. So that 10 is actually a variable. It changes. So what we know is that this ratio of x over 6, so our similar triangles, x over 6, is equivalent to the ratio, or the similar triangle, x plus y over 16. This is why this gives people nightmares. Okay. And the distinction here is that the length of the shadow is that simple x, that simple bit right in here. But the distance of the tip from the pole is that whole entire length. So it's all the way from here to there. And that becomes critical because the shadow is changing at a rate of dx dt, whereas the tip is changing at a rate of dx dt plus dy dt. Then, when we go ahead and try to figure this out, we will be able to figure out both the rate at which the tip of the shadow is moving and the rate at which the length of the shadow is moving. When we go ahead and try to figure that out, and we can simply solve for dx dt, using what we know about dy dt, and dy dt, oh, he's walking away from the pole, so I actually had my arrow backwards, and that would actually be, I'm sorry, dy dt would be 5, so 10 dx dt equals 30, and dx dt would be 3. So the rate at which the length of his shadow is moving from the base of the light is 3 feet per second. And all we need to do is add our two rates to find the answer to A. I think that's another part that's confusing about this, is that oftentimes you have to do B before A. So we add our two rates. We've got 3 feet per second and 5 feet per second, and we end up with 8 feet per second. Doo-doo. And that is what I have for you today. I hope that was not too onerous. I'm so sorry it was so long. I keep promising myself I'm going to try to bring these down below 30 minutes, and I haven't succeeded. I really want them to be 20 minutes. Sorry, guys. Y'all take care. Bye.